Ha ha. Ha ha. What a guy. What a guy. Well, you need something on the board here. Is that screen on? Huh? Hold on. Come on, we got the blue screen of death here.
Jump.
Jump how high? All right, there we go. All right, we're cooking now. All right, well, no, I'm going to show you this today, too. What this is if you go to Digilent's website, all right, you guys have used the EE boards, right, in circuits. Well, this is it is a great scope. I mean, digital, analog. You got couple of scopes on here. 16-channel analyzer. I had to pay like $270 for this thing. If you're a student, you get it for $99. I mean, but if you're ever thinking about going into embedded engineering, it's a beautiful thing to have. I was sitting in my home yesterday. All you do is plug it into your USB port, and you got a fully functional oscilloscope, the logic analyzer, all 9 yards are sitting right there. I mean, it's and I'll show you. I'll demonstrate it today too. All right, because I was using it yesterday, as a matter of fact. All right, so we're going to do I/O programming. That's the whole idea here. I mentioned this the other day. These are your P and B ports right here. All right, on the quad flat package. And your port Bs. I'm going to be using these extensively during this part, port D and port B. I'm going to use port B. I'm going to tie 8 LEDs to it. Over here on both of these ports, you have a this is, I believe, 3.3 volt VCC and ground on both of these also. All right, so those 2 extra pins sitting there are for VCC and ground. And I'm going to tie some switches into this guy over here on the right. And I'm going to be just using a 8-pin dip switch. I'm going to be moving that up and down. I'm going to turn some LEDs on over here. So I'm going to show you how to use these ports as not only outputs but also as inputs. Okay. And your lab this week will be using stack and simulating I/O. Next week you're actually going to tie some LEDs and stuff up to here. All right. Start doing some real I/O. All right. So port D on your quad flat package is tied over here on those pins on the butterfly board. All right. So we're going to be working down here with these I/O registers, which are sitting right after. These are your special function registers that are down here. So that's what we're going to be looking at. And this is just out of page 21 of the manual. So we're going to be working with, again, it's nice that you've got, the butterfly board is just a neat little thing where you've got all these things tied in with the joystick, the speakers, and all that stuff. Right now, we're just going to work with port D and port B. All right. You have to remember that these ports are shared also with the speaker also. I think I ran some code on Friday where you heard, one of the LEDs was attached to it. I think one of the, and this is the example, was tied to the speaker also. So when you fired up that LED, you heard the speaker go off. All right. All right. So what we're doing is we're going to be doing outs and ins. Okay. Out now again. There's 2 ways you can output something from a general purpose register. All right. So you're going to have your general purpose register here with some 8-bit number in it. Okay. And then I can out it to a specific address that's going to address one of these I/O or memory spots. All right. The nice thing, what Atmel set up also, instead of memorizing what all these addresses are, if I want to out 8 bits to any of my ports, port D, B, or whatever, you just set up the data direction register for that port, and then you're just going to out it out there. All right. So this is one way, so I don't have to remember what the address is for my data direction register, which is going to set up which way am I going with this, 1s and 0s in there. The same thing over here, I can take, I can see this battery's dying on this laser pointer, but all right. You can have an address, so like I can grab something from an I/O port and then bring it into one of my general purpose registers, or if I want to just grab something from port C, all 8 bits on port C and bring it into a general purpose register, I can just use this. So instead of memorizing all the addresses for the ins and outs and the data direction registers, you could just use the terms there, all right? So what we basically have is you have port control registers. I can set up the direction for each one of the pins on the I/O port. If I set it equal to a 1, it's an output. If I set it equal to a 0, it's an input. Control the output status pins, all right, for port X. This one also controls a pull-up resistor also when you're using the port as an input. And then I can read in from the pins on, and this little X means any one of the ports, A, B, C, D, E, or F. We're only working on the butterfly board with port B and port D, okay? And so each of the data direction register, that's what DDR stands for, data direction register. It's an 8-bit, all right? I can select each one of those bits to correspond as an input or an output. So if I set bit 7 to a 1, pin 7 on this port will be an output. If I set it to a 0, it's going to be an input. Then I have my port X register here, and then I have my pin ins, all right? So I can output here and input through here, all right? So that controls the direction, all right? So again, we have, they're designated as port X, DDRX, and pin X, and it could be for any one of my general purpose registers. All right, so if I set up, guys, can you keep it down over there? If you guys want to carry on a conversation, please. There's other people around you, all right? If I set up the data direction register, in this case as 0, 1, 1, 1, 1, 0, 1, 0, 1, this 0 forces that pin to be an input. This 1 forces that pin to be an output. This 1 forces that pin to be an output, and so forth. All right, so you can select. It's nice that you just don't have to force all the pins to be an input or output. You can select each one of them. All right, and basically it's pretty straightforward. All right. So making a pin go high or low, you've got basically two ways I can do this, all right? In this case, if I have my port X register set as 0, 1, 1, 1, these set of bits here, and I'm going to output, all of these guys will be sitting as an output, okay? So if I have LEDs attached here and here, they'll start lighting up here, here, and here, all right? Now, we shall see when we're doing inputs, all the pins are active low. All right, so when I ground a pin, and I'll show you when I ground a pin, that's when it actually assumes that it's active low. All right. So here's what happens. Here's what you have on your port. Effectively, what you have here is a tri-state switch. All right. Everybody familiar with tri-state switches? It's not an operational amplifier. What this happens here is this tri-state switch works this way. If this happens to be a 1 right here, this becomes a short circuit. So whatever is here appears out here. If this is a 0 here, this is open circuit. Okay? It's floating. It's in what is called a high impedance state. All right? So what we have here, here's physically the pin that's sitting on the butterfly board. Here I can write out to this port. If I set this data direction register here for this specific pin to be a 1, there's a short circuit right here. All right? So whatever I write here will appear right out here. Okay? So that's forcing that pin to go high if I indeed put a 1 here. All right? If I set the data direction register equal to a 0 for this pin, this is open circuited. I can then input something back into there. Okay? So it just gives me the control. So the data direction register is basically the enable on this tri-state switch. Okay? That's an enable. All right? So that's basically what you have. To read data present at the pins, we should read the PIN in registers. We're going to be reading something in here. And this is going to be active low, so if this is grounded, this will give me a 1 here. Yeah?
Is there another switch in the pin in line? Or I guess the question is, if we set it as an output port, will the pin register then follow whatever we set to the port register?
Yeah, probably should, yeah. I would think so. Because whatever you're writing here is going to appear here. But then again, remember, I'm writing out.
Yeah.
I'm not reading in.
Yeah.
Because the data direction register is set up.
Yeah, I was just curious if
Yeah.
I were to set the port and then read the pin, if they were to be the same.
Yeah.
Okay.
Be aware that, yeah, I think this is just about done. Must be noted that bring data into the CPU, we read the contents of the pin X register. When we send data out, we're using the port X register, okay? All right, here's what's going on when I'm gonna input some data in there. There's what we call a pull-up resistor is sitting up in here, all right? Now, this is something that we picked up when we started using this guy last year, that you have to set these guys, you want those pull-up resistors to be active, all right? What effectively you have is VCC here is sitting next to, that's exactly where VCC, that VCC is this VCC right here, these guys right here, okay? VCC and ground there, okay? All right, and so what you have here, if I have port, whatever port I'm working on, C or B, and whatever pin I'm working on, that's what X stands for the port that you're working on, N is the actual pin number. So each one of the pins has a pull-up resistor that's sitting in there. So what you effectively can do is you can control this pull-up. We typically always set that. All right, so when I'm reading something in, always set up those pull-up resistors. All right. What effectively is happening here is if I ground this here and this is here, all right, that effectively, if I ground this pin here, I then have VCC, that's going to activate that pin, all right? You'll see this. I'll run this for you. You'll be a little bit clearer, all right? So in cases in which nothing is connected to the pin or your connecting devices, they have a high inputs impedance, the resistor pulls up that pin, okay? That's effectively what is happening there. So let's see, there's a pull-up resistor. If we put ones into the bits of the port X register, the pull-up resistors are active. And again, when they're not, you're in a high impedance state, which means this guy is now open here. Okay, so that guy is open circuited. And again, just as a note, it's been our experience for these Atmel I/O ports that in hardware, and when we use the pins as an input, so you always activate those pull-up resistors. Okay, it's just something that you do before you start reading it. And here's effectively what you have. You have port X here and DDRX. If the data direction register is set equal to the 1, okay, set equal to the 1, so therefore I'm outputting stuff. If my port X happens to be a 0, well, I'm going to output a 0. It's going to be ground. If I have port X happens to be a 1, I'm going to output a 1. If the data direction register is a 0, I'm in a high impedance state unless I activate the pull-up resistors, all right? So in effect, if port X is a 0 and DDRX is a 0, that switch is open circuited on the pull-up resistors. Okay, they're not activated. All right. If I force that to be a 1, I'm using it as an input, and I'm activating my pull-up resistor there. Okay. All right. So we have basically you have the port X register. If we set it up, I have basically set up as all inputs, all right? Now here I have this switch is open, so that pull-up resistor is deactivated. This one is 0, that's deactivated, and this one is 0, that's deactivated. Okay, so those guys are all, generally, they're going to be left in a high impedance state there. Okay. So when you read something in, you're going to use the pin in. I mean, that's what it is, pin in and just give it the port. And it'll give you an 8-bit read. So therefore, if I have sitting on that port, that binary number, that will appear in that register when I read everything in. All right, let's see, we're going to, okay, so in this case, we're going to present data at the pins of port C and send it to port D indefinitely after adding a value of 5 to it. So what we're going to do is we're going to load up, again, you have to load up your general purpose register with the 8 bits that you're going to assign for the direction for that port. So in this case, we're going to have just FF. So now I'm going to force out to the data direction register R16. All right, so that forces now the data direction register for port B is now going to be an output port. For simulation purposes only, I'm going to initially set up port C to be an output also because I want to write something to it. Effectively, what I'm going to do is read something from port C and write it to port B and then add 5 to it. All right? So what I'm going to do is just set up, I have to set up some test data first, so that's what I'm going to do here. So now I load up R16 with some binary values, and then I'm going to output them out to port C. So I'm activating port C to have this sequence of binary numbers on it, okay? So pin 7 is going to be high, 6 is low, 5 is low, 4 is low, 3 is low, 2 is high, 1 is low, and the 0 is high, okay? And then I just output them out there. Now I load up the data, I'm going to load up the register R16 with all zeros, and then I'm going to out the data direction register. Now I'm forcing port C to be an input port, okay? And here I have just a label I'm going to in, so I'm going to grab something from pin C, and it's now going to go into R16. I'm going to load into R1, just the number 5, and we're just going to add R17 and R16, which adds the values that I've read into pin C onto R16. And now I'm going to output them to port B. Okay, and then we're just going to infinitely loop in here. Okay, it's just an example on how you set up the registers and how you set up the direction port. I don't know why this keeps repeating. All right, so after I do this, so as I simulate this, we come down. Or actually, let's do it. Bring up your Atmos Studio. Let's copy the code. It's easier to see it. You could run this on any one. Let's do the 169. All right.
You can run it on the 169?
Yeah.
Even though you're using port C?
Oh, it's running on the 2560. Yeah, sorry about that. Or the 32. Either. Oops.
You on the slides that
Does the 169 only have 2 ports?
You only have, on the butterfly board, you have access to port C and port D. That's, if you go back to here, that's what I was trying to show you. That's right here. Those two. That's what physically you have, you can get your hands on.
That's why we have to use the 25.
Yes, because this example, or the 32. Or the 32, yeah. Let's just build this guy. Yeah, we can sing this guy. Now, what you want to do is you want to pick your I/O view here. So just pick your I/O. Slide that down. Let's look at port C. There's my port C. Actually, you can look at port B first if you want. These are the physical addresses for the for pin in. It's 23, 24, and 25. But you don't need to memorize that because that's going to go, that's right in here. In the include file, it takes care of that for you. So you don't have to memorize that the address for that is that. Okay? It's just saves a couple of the neurons from getting burned out, right? So here we're just going to single step through. So now we're going to output it, and here you can see you just loaded up all the pins for the data direction register from port B or high, which is now going to force them to be output. Yes?
How do you get into the I/O view?
You can, there's down here,
Alright, mine doesn't have that in
All right, then go up here and click on that one.
Okay.
You got it? Everybody got the IO view? All right. Yeah, these ones up here control this window also. These guys, so if I want to go to memory, you can go to memory, you can go to the, you know, any other ones over there too. All right, so if you single step through, now we're going to go look at port C. And then we're going to output some bits to port C now. Now you're going to see that bit pattern that we set up here. Pin 7 is high. 6, 5, 4, 3 are low. 2 is high. 1 is low. And the 0th one is low. Or high. Okay? So that's just the data that I want to set up on port C to read in. All right? So that's the reason why I had to do this. Out DDRC and load into R16 that. So it gave me something to read in. If I didn't do this, there's nothing to read in. There's nothing active on that port. Okay? All right, now what we're going to do is we're going to now force, that's what this is going to do now. After I've written to it, I'm now going to force that port to be an input so I can read from it. So that's why I set up that R16 to have twos, you know, all zeros in it. So now we forced it, and if you notice that all these are going to be outlined in red. Okay, that means we've changed the status of those pins. They were changed from inputs or outputs to now inputs. Okay, I think you were asking me about that, Miles, right? So previously they were all red. Now they're just outlined, and it's showing you that they have changed from the previous state.
Does the blue mean that they haven't changed?
Blue, they're staying. These have not changed. Right, these have not changed. Now we're going to read those pins. We're going to read them in. So I'm going to into R16. Now, if you look, let's go over here to the processor view. Go to the processor view, come down, and you'll notice that the 8.5 that was written to port C is now resides in R16. We have simulated. We've only simulated this. We set up port C to be an output. We've written something to it. Then we set up port C to be an input. And then we just read from it into R16. So all I'm doing is setting up I need to set up some test data because I don't have it in hardware. I need to do something in port C. All right? So the contents of port C have now been read into R16. All right? Right here. Now we're just going to we're going to load in 5 into R17, whatever. It's just an example. Then we're going to add those guys together. And if we go look at, now we're going to output that result to port B. So if I go back to my I/O view, click on port B, you can see it's set up as outputs. Okay, they're all, the data direction register for port B is all high. And now I'm simply going to, I take the number that I had, the 8.5, that is in R16, we added 5 to it, and now we're going to output that to port B. Okay? Rachel?
So, I don't know if this is a specific problem, but my pins didn't change at all, only my ports changed along with it.
What do you have there?
I have, everything is fine except for the pins didn't also go to 8A, they stayed at 0 to 0. I don't know.
No, that's port B is an output.
Right, I know, okay, but yours pin B changed with it for some reason.
It follows it.
Oh, okay.
That's what you were asking before.
Okay.
Notice the pin
Oh,
B?
right.
Yeah.
You see it?
Right, because of the
Oh, hold
raw
it.
state.
Okay, but where are you at here? You have 8A.
No, just pin B just didn't follow port B. I'm sorry, if this is specific, then.
All right, I'll have to take a look at that.
Okay.
All right, is everybody same page? Okay. And then you just, we could just keep doing this over and over again. But I just wanted to show you how you can simulate, you're gonna be doing this in lab this week, simulating those I/O pins. So in order to, if you're gonna read something in, again, if you're gonna simulate a read in from an I/O port, you first have to set it up to be an output port, then you have to write to it, and then you set it up as an input, and then you read from it. You get my drift? You got to set up to be an output first. You got to write. There's something that has to be activated on the port. So that's what this is doing here. I'm setting up the data direction for PID for port C to be an output first. Then I write to it. Then here's where I write to it, and then I set up it to be an input, and now I'm going to read from it. Okay, Jake.
I went through it again. It has, for port B, it has all of the bits as blue or gray. Why don't they change back to red and high?
Where are we at here?
If you just run through the program again, so your port B after that, now it says they're all blue. I thought that meant low.
No. They have not changed state.
Oh,
They
okay.
have not changed state. Right. They have not changed any state. All right. Now, and the reason is, these aren't going to change because I'm just the same number. I'm just putting back. I'm reading in that 8.5, and I'm adding 5 to it. And I'm writing it out again.
Yeah.
So it hasn't changed state. It will go red when they change state. These are still high.
Yeah.
They're still high. All right, but they haven't changed state. When they change state is when you'll see it. All right. Well, here, let's do this. Let's stop it. Let's go in here. Let's see. We had our 16 17. Let's do an out. Port B. Let's do this. 0 1 1 0 0 0 0. Oh. It's case sensitive. I'm gonna have to read something into a register first. That's right, yeah. So I'm gonna go, let's do this. LDI, R20. Do this. That's right. It has to be, when you're using the out or the in command, it has to be a general purpose register first. Let's do R20. That. This should do it. There you go, all right? So now, Jake, now we should be able to see it change, all right, when I go through. All right, that sets up the data direction register. Now we set up port C. All right, there's the original one, all right. Now we're going to load it in, and we're going to output. Those have changed, okay? I've changed them all, okay? If I come back and do it again, there it is, okay? All right.
Pin B and port B always have the same values?
Can,
Do pin B and port B always have the same values?
if I'm writing out to it, it will follow it.
Okay.
Yeah. All right, just these couple of slides explain what's going on there. Okay. So again, the status register on port B. This is the I/O address. This is the physical address in memory. Okay, that is the physical address in memory. I/O address, physical address. I/O address, physical address. Okay, and they are 8-bit registers, obviously. Okay. And if you go down and look in the LSS file, if you go down and look in it, you'll see that these are set up. 3, 4, and 5 are set up at the proper I/O addresses. Okay, it forces it. It's just that that's the way it's set up. Yeah.
Let's say we knew that we had a specific element like connected to port B, could we rename it to be something that we wanted it to be, like LED port or something like that?
No. These are very specific. DDRB, pin B. Like you can't call it LED pin B.
Okay.
It's not going to happen. All right, let's see. All right. To access I/O's registers, there's a special mode called I/O direct addressing, and that's what I'm doing. I'm doing some direct addressing here. I'm going to load a 25 and an R18, and I'm going to directly address that I/O port. Okay. So port C happens to be sitting right at 08 is the I/O address. All right. So that can be a direct addressing mode where you got the NOP code, the register, and the bits that you're going to put in. Okay. All right. If I'm going to read something in, I read it into a general purpose register, and I give it the I/O address. Okay. Or I could, if I don't want to give it the I/O address, I can just have port B, port C, whatever. But if I'm going to give it the I/O address, you physically give it the I/O addresses here. Okay? I can out the same way, out from a general purpose register to an I/O address. Okay? And again, this would be physically the I/O address for the status register. This would be the I/O address for the stack pointer high. And if I go to 3D, it would be the stack pointer low. Here I'm going to output. I'm going to take the contents of R12 and I'm going to load it into the stack pointer high using the out. I can take the status of the status register and take it into R15 into any one of the general purpose registers. All right, write a program to add the contents of pin C I/O register to the contents of pin D and store the location into RAM at 90. All right. So here we take the contents of pin C, will come into R20. Take the contents of pin D into R21, add them together, store that result into that memory location. It's pretty straightforward. And again, just showing you from the LSS file, these are the I/O addresses that are all in. Okay. All right, so we're going to take 55, send it to port B, and include the register name. So here we're going to load up. Port B is going to get loaded up, or R20 is going to get loaded up with all ones, because we're then going to force data direction register to be all ones, so it's an output. Data direction register is set up. I now send the data into R20 by 5, and then I simply output port B, R20, and that writes it to it. It's really a nice way to get at it. There you can see it right down there. Okay? Just setting it up. Let's see what I'm doing here. It just has, I'm including the I/O addresses here instead of using the names. All right, so I'm setting up the port B data direction register right here. That's sitting at I/O address number 4. All right, I load up the 55 and the R20 and I output it to 5. Okay, so that's going to write out to port B. Just instead of using port B's name, you're just using the I/O address for it. Okay. Let's see what we got here. Here I'm going to, again, we're going to use the I/O. We're going to put in an A3 in the R20. R20 is going to go into 04 with 24, which is that direction register. Put the 55 in, and then just output, and then store it. Okay. And that allows me to just bang, write that thing right there. And whoops, click on the trigger there. So, and you can physically see it down when you look in IRAM. Okay, you can physically see where you're writing that to in IRAM. All right. That's the address for it. Okay. All right. I wanted to show you some videos. Actually, this was just some more examples. Toggling the I/O pins. That's pretty straightforward. If I set up the port B to be an output, load the 55 in there, output port B. then I calm it. What that's gonna do is it's gonna force the 5.5 to be toggled. So that should be an AA, all right? So you're just toggling it, and then I jump back. All right, so here I'm gonna show you some real hardware, all right? I have some videos that are all loaded up on your, if you go to TU Portal and then go to the videos, there's a whole bunch of them in here. And let's just go to, should have some audio. No audio?
Oh, it's not good, not the app, right?
Give me no audio. Oh. Barely hear it. Let me just stop this for a sec. What I have here, here's the butterfly board. It's sitting in that little, nice little 3D printed case. The battery sits inside of here underneath there. Has anybody printed theirs out yet? Nobody? All right. You might want to do that. Because, I mean, when you have these batteries sitting out, they fall off of that thing and you have to resolder it all the time. Here's my port B right here. So what I did was I took just a whole bunch of LEDs. I put eight LEDs are sitting on there, all right? And all I'm doing is writing to the port, I'm forcing it high, then I force it low with a delay of 1 second. So I'm going high, low, high. That's all I'm doing, is just writing to it. High, low, there. All right, let's go. Here I sequentially blink them. So here I'm going to fire up the first one, shut it down. Fire up the second one, shut it down. Fire up the third one, shut it down. So it comes back. This one's sitting on, so this LED down here is sitting on port B, pin 0, which is the first one there. All right, so it's port B, pin 0, turn that one on, then shut it off, and then go up here. And then I'll show you how to do the I/O stuff with those switches there in a second. And there's a delay of a second in between them, just so you can see it. You know? There's my genius son over there playing his video games. Smoked a big doobie that morning, I think. He wants to be a doctorate of physical therapy. That's our computer room, by the way, on Sunday mornings. So, let's see where we at here. All right, let's get back over to scoping the LEDs. I'm going to show you how to scope them. That's using this guy right here. Sorry. Sorry about the audio. You have a 2-channel scope here. This is actually, you guys remember waveforms? This is the screen board. You can see it up top there. Let me just. So as this thing's coming across, oof, it's a little blurry, but I think you'll see it when I start running it again. You'll see this is high, and each one of these is two seconds per division. So I'm turning it high for 1 second, low for 1, so the period of it's 2, and you can see it on there pretty good. Watch as that cursor's going across. A little bit grainy here, but there it goes, high, low, low. And then I looked at it on the, actually on the meter, so I hooked up a fluke meter to it. There it goes, high. There it goes, low. So again, it's just a nice, I mean, it's for 99 bucks, it's worth its weight in gold. And there's the infinite images. If you point your webcam at the screen, it's capturing it. Yeah, I haven't seen this too often, but. Ah, mistake. All right, well, I'll let you go play. All right, so that was my morning yesterday. Watching the Ryder Cup get smoked. All right, IO bit manipulation, 1 switch and 1 LED. All right. All right, so here's the circuit that I had. I grabbed VCC, had a resistor, a switch, ground. This went into P. I forget which one. Let me just bring that up. I think I have a schematic here. Yeah, there's the code for that stuff. It's sitting there. There it is, right there. All right, so I had a 4.7K resistor. VCC I tapped off of either port B or port D, and then I just had a switch here, all right? I then had a, I think it was 270 ohm resistor and an LED here. So I'm going to read into port D, pin 0, and then I'm going to write out. So when this switch goes active low, it will be right here, active low, and then I'll turn the LED on over here, okay? So that was the idea. So here I'm just using, I have the 8-pin dip switch, but I'm only using 1 switch, all right? And then I just borrowed one of the 8 LEDs that I had on pin or port B. It happened to be PB2, okay? All right, so what you see here is, here's my dip switches over here. I could have used any one of these. If you notice, all these little yellow wires, ground is on this rail back here. All that is ground back there. Here's my switches here that I can throw, and I think I only used one. It was this switch here, the first one. All right, so I'm on port D, pin 0 is what this is tied to. And I actually have the scope on it also. I'm going to light up. This is port B, pin 0, pin 1, pin 2. All right, so we're going to write to the third LED, which is on pin number 2.
All right, I have the butterfly board connected to these LEDs. Those have 7 switches over here. Port D is going to be used as an input. In particular, I'm going to use
Now, if you notice here, this guy here is this yellow wire is going over to the switch, okay? That yellow wire. So I'm reading that, that's where it is. It's right off of my switch, okay?
PB0 as an input off of that switch right there. I have multiple LEDs connected to port B, but I'm only going to activate
when we activate the switch, that LED should turn on, okay? That one will turn.
Port, D down to ground, right now, I'm at is
Right now I have the Fluke meter is on that port and it's a VCC, which is 3 volts on that port. All right, so I got 3 volts sitting on there. So again, the switch is open. This is sitting at 3 volts. Okay, so I basically took that with the switch open. I was going right to the meter, and it's reading 3 volts. When I throw this switch down, what's the meter going to read? Luke, when I close this switch, what's the voltage going to be here to here? What is voltage going to be? Close that switch. What's the voltage between these 2 points? 0. It's grounded. It's short. All right. It's grounded. And you're going to see it.
So, when we activate this switch,
I'm trying to hold that my webcam. I should have grabbed my son, but he was intently. There it is. He don't want to help his old man. So we closed the switch, it grounded that pin, it's active low, and now it had written to pin PV2. So that's simply doing an IO. If I had a burglar alarm attached to there, I could instead of having an LED there, I could have a buzzer. You know, send out a. All right. Have a good one. The assignment's up for chapter 4, so it's fair game. The exam will be October 9th.